Welcome, beginner game developers, to this comprehensive guide on creating dynamic enemy AI in Unity. Today, we'll dive into the essentials of pathfinding and state-based logic, fundamental concepts that will elevate your game development skills. This tutorial is designed to provide a step-by-step approach, ensuring you grasp each concept thoroughly and can apply it to your own projects with confidence. We'll explore how to make your in-game enemies intelligent and reactive, creating a more immersive and challenging experience for players. Understanding AI is crucial for engaging gameplay, as it breathes life into your virtual worlds. We'll cover how to make enemies move intelligently through complex environments and react realistically to player actions, making every encounter feel dynamic and unpredictable. This involves not just movement, but also decision-making processes that mimic real-world behaviors, enhancing the overall player experience significantly. Our journey begins with setting up the Unity 3D engine, the powerful platform we'll be using. We'll ensure our project is perfectly ready for AI implementation, starting with the creation of a brand new 3D project. This initial setup is vital for laying a solid foundation, allowing us to integrate AI components seamlessly and efficiently as we progress through the tutorial. Next, we'll introduce the concept of NavMesh, Unity's incredibly powerful built-in solution for pathfinding. This sophisticated system allows AI agents to navigate even the most complex environments efficiently and intelligently, avoiding obstacles and finding optimal routes. Understanding NavMesh is a cornerstone of creating believable AI movement, as it handles the intricate calculations of traversable surfaces and obstacles automatically. To enable pathfinding, we'll bake the NavMesh. This crucial process analyzes the scene geometry to determine all walkable areas and identify any obstacles, creating a detailed navigation map for our AI. Baking the NavMesh is a one-time operation for static environments, and it's essential for the NavMesh agent component to function correctly, providing the AI with the necessary data to move intelligently. Now, let's create our enemy AI agent. We'll add a simple 3D capsule as our placeholder enemy, which will serve as the visual representation of our AI. Crucially, we'll attach a NavMesh agent component to it, which is the core component that allows our AI to utilize the baked NavMesh for pathfinding and movement. This component provides a wide range of configurable properties to fine-tune the agent's behavior. With the agent set up in Unity, we now need a script to control its movement and behavior programmatically. We'll open Visual Studio, our integrated development environment, to begin writing our C# code. This script will be the brain of our AI, dictating how it interacts with the environment and the player, bringing our simple capsule to life with intelligent actions. Our first step in the script is to reference the NavMesh agent component we just added in Unity. This allows us to programmatically control the AI's navigation, setting destinations and managing its movement parameters directly through code. We'll typically do this by declaring a private variable of type NavMeshAgent and initializing it in the start method using getComponent, ensuring our script has access to the agent's functionalities. Next, we introduce the fundamental concept of state-based AI. This powerful approach allows our enemy to behave distinctly and appropriately based on its current situation or internal state. Instead of a single, monolithic behavior, the AI transitions between different states like idle, patrol, chase, or attack, each with its own set of rules and actions, making the AI much more dynamic and believable. To implement state-based AI effectively, we'll define an enumeration for our AI states: idle, patrol, chase, and attack. Using an enum makes our code incredibly clean, readable, and easy to manage, as it provides a clear, descriptive list of all possible states our enemy can be in. This structured approach is a best practice for managing complex AI behaviors. Let's start by implementing the idle state. In this state, the enemy will simply stand still, perhaps looking around or performing a subtle animation, conserving energy and waiting for a trigger. This state represents a period of inactivity or observation, and it's often the default state an enemy begins in before detecting a player or other stimuli. The patrol state involves the enemy moving systematically between predefined waypoints, simulating a guard or a creature traversing its territory. We'll set up an array of transform positions for these points, allowing us to easily define a patrol route within the Unity editor. The AI will sequentially visit each waypoint, creating a predictable yet essential behavior pattern. In Unity, we'll create empty game objects to serve as our patrol waypoints, strategically placing them along the desired patrol path. Then, we'll assign these game objects to the enemy script's public waypoint array in the inspector panel. This visual setup makes it intuitive to design and modify patrol routes without needing to change any code, offering great flexibility during development. The core patrol logic will involve instructing the NavMesh agent to move to the current waypoint's position. Once the agent reaches its destination, we'll advance to the next waypoint in the array, looping through them to create continuous patrolling. This ensures the enemy follows its designated route, providing a consistent and observable behavior pattern for players. Now, for the chase state, which is where the action often begins. When the player enters a certain detection range, the enemy should immediately transition to this state and actively pursue them. This state is critical for creating dynamic encounters, as the enemy's primary goal becomes closing the distance to the player, often increasing its speed and focus. We'll implement a detection radius using physics.overlap sphere to efficiently check for the player's presence within a specified range around the enemy. This method is highly optimized for checking for colliders within a spherical volume, making it perfect for determining if the player has entered the enemy's line of sight or hearing range, triggering a state change. If the player is successfully detected within the radius, the enemy's state will immediately transition to chase. In this state, its destination will be continuously updated to the player's current position, ensuring the enemy always moves directly towards the player. This constant updating creates a relentless pursuit, making the chase feel dynamic and responsive to player movement. Finally, we arrive at the attack state. Once the enemy is close enough to the player, specifically within its defined attack range, it should stop chasing and initiate an attack sequence. This transition signifies the enemy has successfully closed the distance and is now ready to engage, often involving a specific animation or damage-dealing action. We'll define an attack range, which is a crucial parameter determining how close the enemy needs to be to the player to initiate an attack. When the distance to the player falls within this predefined range, the enemy's state will transition from chase to attack. This precise distance check ensures the enemy only attacks when it's truly in striking distance, making the combat feel fair and logical. In the attack state, the enemy might stop moving entirely to focus on its attack, play a specific attack animation, or deal damage to the player. For simplicity in this tutorial, we'll primarily focus on having the enemy stop its movement by setting agent a stopped equals true. This action signifies the enemy is committed to its attack, preventing it from overshooting the player while attacking. To manage these distinct states and their transitions, we'll use a switch statement within our update method. This structure allows us to call the appropriate function for each state, ensuring that only the logic relevant to the current state is executed. This makes our AI code organized, efficient, and easy to debug, as each state's behavior is encapsulated within its own method. Remember to consider state transitions carefully, as they are key to fluid and believable AI behavior. For example, an enemy in the attack state might need to transition back to chase if the player moves out of its attack range. Implementing these return conditions ensures the AI doesn't get stuck in a state and can adapt to changing combat situations, making it more robust. Testing is absolutely vital throughout the AI development process. Play your scene frequently to observe enemy behavior in real time and fine-tune parameters like speed, detection range, and attack range. Iterative testing allows you to identify and correct any unexpected behaviors, ensuring your AI acts exactly as intended and provides the desired challenge and immersion for players. You can significantly enhance this basic AI with more complex behaviors, pushing the boundaries of what's possible. Consider adding features such as dynamic obstacle avoidance, sophisticated flanking maneuvers to outsmart the player, or even group AI where multiple enemies coordinate their actions. These advanced techniques can transform simple enemies into formidable adversaries, adding layers of depth to your game. Experiment with different NavMesh agent settings, like speed, acceleration, and angular speed, to give your enemies unique movement characteristics. A slow, lumbering enemy will feel very different from a fast, agile one, even with the same core AI logic. Adjusting these parameters allows you to create a diverse cast of enemies, each with its own distinct feel and challenge, enriching the gameplay experience. Consider adding visual cues for your AI states, as this greatly enhances player understanding and feedback. For instance, changing the enemy's material color when it transitions from patrol to chase, or displaying an icon above its head can instantly communicate its current intent. These visual indicators make the AI's behavior transparent and engaging, allowing players to react more effectively. This foundation in pathfinding and state-based logic is a powerful starting point for creating intelligent and challenging enemies in your games. By mastering these core concepts, you're well on your way to developing AI that not only navigates effectively, but also makes strategic decisions, providing a truly engaging experience for players. This knowledge forms the bedrock for all advanced AI systems. Keep practicing, keep experimenting with new ideas, and soon you'll be crafting AI that truly brings your game worlds to life with believable and dynamic characters. The journey of AI development is continuous, with endless possibilities for innovation and creativity. Embrace the learning process and watch your virtual creations evolve into intelligent entities. Thank you for joining this comprehensive tutorial on enemy AI in Unity. We sincerely hope this guide empowers you to build amazing, intelligent AI for your Unity projects, transforming your game ideas into interactive realities. Happy developing, and may your AI creations be both challenging and incredibly fun for players to encounter.